Imagine traveling so far from the sun that Earth becomes invisible, just another star in an ocean of light. Out here, in the solar system's twilight zone, two giants drift in near silence. One rolls through space on its side like a cosmic bowling ball. The other screams with winds faster than the speed of sound, powered by forces we still cannot fully explain. These are Uranus and Neptune, the ice giants, and they are nothing like anything else you have ever encountered. For the next hour, we journey together to the edge of everything, where planets break the rules and physics becomes strange. Close your eyes if you wish. Let your mind travel where spacecraft have ventured only once. Welcome to the Forgotten Worlds. Our journey begins in the outer darkness, where sunlight arrives weakened and pale. We are leaving behind the familiar worlds of rock and gas, traveling towards something entirely different. You might think of Jupiter and Saturn as the giants of our solar system, and they are magnificent beyond measure. But out here, beyond the orbit of Saturn, two other giants wait in the cold. They are smaller, yes, but they are stranger. They are Uranus and Neptune, the ice giants, and they represent a kind of planet we are only beginning to understand. As we cross billions of kilometers, the sun behind us shrinks to just another bright star. Ahead, in the perpetual twilight, two blue worlds beckon. At this distance, light from the sun takes more than 2.5 hours to reach Uranus. For Neptune, even farther out, the journey takes 4 hours. Think about that for a moment. When you see sunlight glinting off these worlds through a telescope, you are seeing light that left the sun before your lunch break. Out here, solar energy becomes a whisper. Yet somehow, impossibly, Neptune rages with the fastest winds ever recorded on any planet. This is the first mystery we will explore together, and it will take us deep into the hearts of these frozen giants. You have probably heard these worlds called gas giants, lumped together with Jupiter and Saturn in the outer solar system family. But that is not quite right. Uranus and Neptune are different in a fundamental way. While Jupiter and Saturn are made mostly of hydrogen and helium, like the Sun itself, Uranus and Neptune are constructed from heavier materials. We call them ice giants, though the name is misleading. There is ice inside them, yes, but not the kind you know. Not frozen water you could skate on. The ice inside these worlds exists under such crushing pressure and searing heat that it becomes something alien, something that should not exist, something simultaneously solid and liquid. The difference between gas giants and ice giants is not just academic. It defines everything about these worlds. It explains their colors, their weather, their magnetic fields, even their very existence. Jupiter and Saturn are like miniature stars that never quite ignited. Uranus and Neptune are something else entirely. They are cosmic laboratories where water, methane, and ammonia are crushed into states that do not exist anywhere on Earth. States we can barely recreate in our most advanced laboratories. As we draw closer, the pale blue disk of Uranus begins to resolve details. It spins on its side unlike any other planet, its rings forming a perfect bullseye pattern around it. Uranus appears serene from this distance, a tranquil world of soft blue-green light. But appearances deceive. This planet was knocked completely on its side by a catastrophic impact billions of years ago. Imagine a collision so violent it toppled an entire world, sending it rolling through space like a ball thrown down a cosmic lane. Even today, Uranus bears the scars of that ancient violence in ways both obvious and hidden. Its rotation axis lies almost parallel to its orbit. Its moons circle the planet's equator, creating that distinctive bullseye pattern. And deep inside, something changed during that impact. Something that explains why Uranus barely radiates any heat at all. Beyond Uranus, another 1.5 billion kilometers farther into the darkness, Neptune waits. Where Uranus appears calm, Neptune seethes. Its deep blue atmosphere churns with massive storm systems, white clouds racing across the surface at speeds that shatter the sound barrier. This should not be possible. Neptune receives 900 times less sunlight than Earth. Its cloud tops sit at nearly minus 220 degrees Celsius. By every reasonable expectation, Neptune should be frozen and dead. Instead, it is the most meteorologically active planet in the solar system. The energy must come from within, from some furnace buried deep in the planet's heart. But what fuels that furnace remains one of the great mysteries. As we position ourselves between these two worlds, the contrast becomes striking. Uranus drifts in pale serenity while Neptune rages in deep blue fury. They are nearly the same size, almost certainly made of the same materials, formed in the same region of the early solar system. Yet they could not be more different. Uranus barely whispers. Neptune screams. One appears nearly featureless. The other displays storms the size of Earth that appear and vanish over years. Understanding why these twin worlds diverge so dramatically is one of the fundamental questions driving planetary science today. The answer may tell us not just about these two planets, but about the nature of worlds throughout the galaxy. Before we descend to explore these worlds in detail, take a moment to appreciate where we are. Behind us, nearly 3 billion kilometers away, Earth orbits the Sun in what we call the habitable zone. Out here, water would freeze instantly. Organic chemistry would cease. Life as we know it could not exist. Yet these planets endure, circling the Sun in orbits that take decades to complete. Uranus requires 84 Earth years for one orbit. Neptune takes 164 years. Humanity discovered Neptune in 1846. It has not yet completed a single orbit since that discovery. These are worlds that measure time on scales that dwarf human lifetimes. Let us explore them together. What makes a planet an ice giant? The name itself misleads. These worlds are not frozen solid. They are not balls of ice drifting through space. The truth is far stranger. An ice giant is defined by its composition. While gas giants like Jupiter contain more than 90% hydrogen and helium, ice giants reverse this ratio. Uranus and Neptune consist of only about 20% hydrogen and helium. The remaining 80% is made of heavier materials that we call ices. But these are not ordinary ices. They are water, methane, and ammonia compressed under such extreme conditions that they become something our everyday experience cannot prepare us for. Something that challenges our very definitions of solid and liquid. Let us descend through Uranus, layer by layer, and discover what lies beneath that serene blue surface. We begin in the outermost atmosphere, where temperatures hover around minus 220 degrees Celsius. Here, methane gas drifts in the upper layers, absorbing red wavelengths of sunlight and giving the planet its distinctive cyan color. But this atmosphere is shallow, only 10,000 kilometers deep. That sounds vast, but remember this planet is 51,000 kilometers in diameter. The atmosphere is just a thin skin over something much more substantial. As we descend, pressure rises rapidly. Temperature climbs. The hydrogen and helium gradually transition from gas to supercritical fluid, a state that is neither liquid nor gas. At about 1,000 kilometers depth, we leave the atmosphere and enter the mantle. This is where things become truly alien. Pressure now exceeds 1 million times Earth's atmospheric pressure at sea level. Temperature has climbed to thousands of degrees Kelvin. Under these conditions, water no longer behaves as water. Methane molecules begin to break apart. Carbon atoms separate from hydrogen. And here, in this hellish environment, diamonds begin to form. Not small diamonds, not gemstones for jewelry. We are talking about diamonds that could grow to millions of carats, slowly sinking through layers of increasingly exotic ice as they descend toward the core. Diamond rain falling through an ocean of hot black ice. This is the reality inside an ice giant. The deepest layers of the mantle, from about 10,000 kilometers down to 22,000 kilometers depth, contain something even stranger. Here, pressure reaches hundreds of gigapascals. Temperature soars above 5,000 degrees Kelvin, as hot as the surface of the sun. Under these extreme conditions, water ice transforms into a phase called supersonic ice. In this bizarre state, oxygen atoms lock into a rigid crystalline lattice like a solid, while hydrogen nuclei flow freely through that lattice like a liquid. The substance appears black rather than transparent. It conducts electricity like metal. It is simultaneously solid and liquid. This may be the most common form of water in the entire universe, and it exists nowhere on Earth. Finally, we reach the core. Here, at the very heart of Uranus, sits a small rocky sphere of iron, nickel, and silicates. It is tiny compared to the planet's overall size, perhaps only half an Earth mass. But it is under pressure that defies comprehension. 700 gigapascals. 8 million times the atmospheric pressure at Earth's surface. Temperature here reaches 5,400 degrees Kelvin. This core formed first, billions of years ago in the planet's birth nebula. As the young core grew, it attracted the ices and gases that now form the bulk of the planet. But something about this core, or the layers above it, seems to trap heat. Uranus barely radiates any warmth into space. The core's heat cannot escape. Neptune's interior follows a similar architecture but with crucial differences. It has a slightly larger rocky core, about 1.2 Earth masses. It has the same layers of exotic ices and supersonic water. It has diamond rain falling through hot black oceans just like Uranus. But Neptune's interior heat flows freely. The planet radiates 2.6 times more energy than it receives from the sun. This single difference cascades through every observable property. It powers Neptune's supersonic winds. It drives the formation and dissipation of massive storm systems. It keeps the atmosphere churning and dynamic. The question that haunts planetary scientists is simple but profound. These two worlds are so similar. Why do they behave so differently? Recent research in 2024 offers a potential answer. Computer simulations show that under ice giant interior conditions, water and hydrocarbons naturally separate into two immiscible layers like oil and water. The water-rich layer floats above a layer rich in carbon, nitrogen, and hydrogen compounds. This stratification may prevent large-scale convection currents from transporting heat efficiently. If Uranus has more pronounced layering than Neptune, perhaps due to differences in composition or that ancient giant impact, heat from the core would become trapped below these boundaries. Neptune's interior might be more mixed, allowing heat to rise freely. The mystery is not yet solved, but we are getting closer. Every piece of data brings us nearer to understanding these alien worlds. One more crucial fact about ice giant interiors deserves your attention. The boundaries between layers are not sharp. There is no ocean surface where you could dive in. No distinct line where atmosphere ends and mantle begins. Instead, everything grades smoothly from one state to another. Gas becomes supercritical fluid, becomes exotic, ice becomes core, rock in a continuous gradient. If you could somehow survive the descent through an ice giant, you would never encounter a moment where you pass through a boundary. You would simply find the substance around you gradually becoming denser, hotter, stranger with every kilometer you descended, until finally, crushed by impossible pressure and seared by stellar temperatures, you would reach the core at the center of a world humans have barely begun to understand. Uranus defies convention in the most visible way possible. While every other planet in our solar system spins roughly upright like a top, with rotation axes tilted only modestly, Uranus lies on its side. Its axial tilt measures 97.77 degrees. Think about what this means. The planet does not spin with its poles pointing roughly north and south. Instead, it essentially rolls along its orbital path like a bowling ball. One pole, then the equator, then the other pole, each taking their turn facing the Sun during the 84-year orbit. This is not a subtle quirk. This is a fundamental reorganization of how a planet relates to its star. And it changes everything. How did this happen? The leading explanation invokes catastrophic violence in the early solar system. About 3 to 4 billion years ago, when the planets were young and space was more chaotic, an object roughly the size of Earth slammed into Uranus. The impact was so energetic, so violent, that it knocked the entire planet onto its side. Computer simulations show that such a collision could produce the observed tilt while also explaining other mysteries. The impact would have expelled most of the primordial heat from the planet's formation. It might have created insulating layers in the interior that trap what little core heat remains. That ancient collision, lasting only hours, shaped the planet we see today. Uranus bears the scars billions of years later. The consequences of this tilt transform every aspect of Uranus. Because the rotation axis lies nearly in the orbital plane, the poles experience the most extreme seasonal variations imaginable. For 21 Earth years, nearly a quarter of each Uranian orbit, the South Pole faces the Sun continuously in perpetual daylight. During this time, the North Pole remains in complete darkness, a 42-year night broken only by starlight. Then, as Uranus continues its slow journey around the Sun, the seasons gradually reverse. The South Pole slides into darkness. The North Pole emerges into light. And this cycle repeats every 84 years, generation after generation, since the planet formed. When Voyager 2 arrived in January 1986, it encountered Uranus during southern summer. The South Pole basked in sunlight. The North Pole lay shrouded in 42 years of darkness. The spacecraft could only image the southern hemisphere. Everything we know about the northern half of Uranus comes from those few hours when one pole happened to be visible. By 2028, Uranus will reach northern summer solstice. The North Pole, dark since 1986, will emerge fully into light. This represents the optimal opportunity for a future mission. A spacecraft arriving during equinox could study the entire planet, both hemispheres, all latitudes. Miss this window and the next optimal alignment does not occur for another decade. Despite this extreme solar distribution, Uranus maintains surprisingly uniform temperatures across its surface. You might expect the sunlit pole to be far warmer than the dark pole, but atmospheric circulation redistributes heat efficiently. Winds carry warmth from illuminated regions to darkened ones. The result is that temperature differences between poles and equator remain modest, only about 10 degrees Kelvin. But here is the puzzle. Uranus holds the distinction of having the coldest planetary atmosphere in the solar system. At the tropopause, temperatures drop to 49 Kelvin, minus 224 degrees Celsius. This is colder than Neptune, despite Uranus being nearly 2 billion kilometers closer to the Sun. The explanation circles back to that ancient impact and its consequences. Uranus barely radiates any internal heat. Recent measurements suggest it emits perhaps 15% more energy than it receives from sunlight, though even this modest figure remains debated. Compare this to Neptune, which radiates 2.6 times its solar input. The difference is staggering. Without a strong internal heat source, Uranus relies almost entirely on dim sunlight for its energy budget. And at 19 astronomical units from the Sun, that sunlight is feeble indeed. Solar flux at Uranus measures only 3.69 watts per square meter, compared to Earth's 1,360 watts per square meter. Imagine trying to warm your home with a nightlight. That is the energy challenge facing Uranus. The magnetic field of Uranus ranks among the strangest in the solar system. On Earth, our magnetic field aligns roughly with our rotation axis, tilted only about 11 degrees. This is normal. Expected. But Uranus's magnetic field tilts 59 degrees from its rotation axis. Even more bizarre, the magnetic field center is offset by 31% of the planet's radius toward the south rotational pole. As the planet rotates every 17 hours, 14 minutes, this off-center tilted field causes the magnetic axis to wobble wildly. The magnetotail, the region where the magnetic field extends into space behind the planet, winds into a corkscrew shape stretching millions of kilometers. Navigating through Uranus's magnetosphere would feel like flying through a cosmic washing machine. Why does Uranus have such a strange magnetic field? For decades, this remained a mystery. Then, in 2024, researchers using supercomputer simulations solved the puzzle. The answer lies in those compositional layers we discussed earlier. The separation of water-rich and carbon-rich layers in the interior creates only a thin outer shell where convection can occur. On Earth and most planets, convective motion throughout a large portion of the interior creates an organized dipole magnetic field. On Uranus, convection in a thin shell generates a chaotic multipolar field. The result is a magnetic field that does not point toward the poles and does not originate from the planet's center. It is a field unlike any other, generated by an interior structure unlike any other. Uranus commands a family of 29 known moons, each orbiting in the planet's equatorial plane. Because Uranus lies on its side, these moons do not orbit around the planet's waist as you might expect. Instead, they circle around what would be the top or bottom if you were looking at the planet from Earth. The 5 largest moons bear names drawn not from Greek or Roman mythology like most solar system bodies, but from the works of William Shakespeare and Alexander Pope. Titania, Oberon, Umbriel, Ariel, and Miranda. These worlds were unknown until Voyager 2 arrived. What it discovered astonished everyone. These moons are not simple balls of ice. They are geologically complex worlds with their own stories to tell. Titania, the largest, spans 1,578 kilometers in diameter, roughly half the size of Earth's moon. Its surface bears enormous fault systems and canyons, indicating this world was once geologically active. Impact craters up to 326 kilometers across scar the ancient terrain. But Titania may harbor a secret. Beneath its icy crust, at the boundary between the rocky core and the icy mantle, a liquid water ocean might exist even today. Tidal forces from Uranus and neighboring moons could generate enough heat to maintain liquid water. If confirmed, Titania would join the growing list of ocean worlds in our solar system. Worlds where life, perhaps, could find a way. Oberon, the outermost major moon, presents a face frozen in time. At 1,523 kilometers across, it displays the most heavily cratered surface of all the large Uranian moons. This is an ancient landscape largely unchanged for 4 billion years. Dark material fills many crater floors, though its composition remains unknown. A mountain nearly 6 kilometers high rises from the surface, and a canyon exceeding 537 kilometers in length cuts across the terrain. Oberon appears geologically dead, a frozen museum preserving the early solar system's violence. But even dead worlds have stories. The craters and canyons map an ancient history written in ice and stone. Miranda defies all expectations. This small moon, only 472 kilometers in diameter, possesses what scientists call the most extreme and varied topography of any object in the solar system. Verona Rupes, possibly the highest cliff anywhere, towers 20 kilometers above the surrounding terrain. If you fell from the top of this cliff in Miranda's weak gravity, you would fall for 12 minutes before hitting the bottom. The surface appears as a bizarre patchwork of different terrains mashed together. 3 distinct oval features called coronae display chevron-shaped patterns found nowhere else. Giant canyons plunge 12 times deeper than the Grand Canyon. What could create such chaos on such a small world? The leading theory proposes that Miranda shattered. A violent impact broke the moon into pieces, which then gravitationally reassembled into the jumbled world we see today. But even more remarkably, a 2024 study suggests Miranda may have hosted a subsurface ocean 100 kilometers thick within the last few 100 million years. This is geologically recent. The ocean might have been maintained by tidal heating from a past orbital resonance with Umbriel. If true, this tiny, shattered, reassembled moon was once an ocean world. Even now, as Miranda drifts in the darkness 19 astronomical units from the sun, liquid water might persist in a deep subsurface sea. Life is tenacious. Perhaps even here, life found a way. 13 rings encircle Uranus, discovered in 1977 when the planet passed in front of a star and the rings blocked the starlight. These rings are extraordinarily dark, reflecting only 2% of the light that hits them. They are darker than coal, darker than asphalt. Most of the rings remain incredibly narrow, less than 13 kilometers wide, despite orbiting 50,000 kilometers from the planet. The brightest ring, called Epsilon, spans 20 to 100 kilometers in width and is confined by 2 shepherd moons named Cordelia and Ophelia. These small moons use their gravity to keep the ring particles from spreading out. Without the shepherds, the rings would dissipate within centuries. The outer rings of Uranus show unusual colors. The new ring appears reddish, while the outermost mu ring displays blue coloration, possibly from freshwater ice delivered by a tiny moon named Mab. These rings are young, likely formed from collisional destruction of ancient moons less than 600 million years ago. That seems like a long time, but in solar system terms it is recent. Dinosaurs still roamed Earth when these rings formed. This tells us something important. The Uranian system is not static. It is still evolving. Moons collide, rings form and dissipate. Even now, billions of years after the planets formed, change continues. The solar system remains a dynamic place. In February 2025, the James Webb Space Telescope discovered Uranus's 29th moon. Designated S2025U1, it measures only 10 kilometers across, making it the smallest Uranian moon ever found. It orbits about 35,000 miles from the planet in a nearly circular path. This discovery, announced in August, demonstrates that even after decades of study, even after Voyager's visit and Hubble's observations and now Webb's unprecedented infrared vision, Uranus still holds surprises. How many more tiny moons orbit undetected in the darkness? How many more secrets does this system conceal? We have only begun to explore these distant worlds. Every new observation reveals how much we do not yet know. We turn now to Neptune, and immediately the rules change. Located 4.5 billion kilometers from the Sun, receiving only 1/900th of Earth's solar energy, with cloud top temperatures of -218 degrees Celsius, Neptune should be frozen and calm. It should be dormant, fed, cold blue sphere drifting silently through space. Instead, Neptune hosts the fastest planetary winds ever recorded. 2,100 kilometers per hour, 1,300 miles per hour, 580 meters per second. This is 1.5 times the speed of sound at high altitude. These are supersonic winds screaming around the planet in darkness. Well, is this possible? The energy must come from within. Neptune radiates 2.6 times more energy than it receives from the Sun. Deep within the planet, the core temperature reaches 5,400 Kelvin, nearly as hot as the surface of the Sun. This internal furnace drives powerful convection currents through the supercritical fluid mantle up into the atmosphere. Heat rises. Gold sinks. The cycle perpetuates. Methane in the upper atmosphere acts like a greenhouse, trapping the rising heat and preventing its escape. This creates what scientists call a sub-zero greenhouse effect. The atmosphere stays warmer than it should based on sunlight alone. And this warmth, this internal heat engine, powers weather systems of unimaginable violence. Neptune is alive in ways Uranus is not. When Voyager 2 arrived at Neptune in August 1989, it discovered a storm system that would become iconic. The Great Dark Spot, an Earth-sized anticyclonic vortex measuring 13,000 kilometers by 6,600 kilometers, dominated the southern hemisphere. Winds at its edges reached that record-breaking 2,100 kilometers per hour. Bright white methane ice clouds formed at the storm's periphery, where gas swept upward into the frigid upper atmosphere and condensed into crystals. These companion clouds constantly formed, raced around the vortex and dissipated, creating a dynamic display. Voyager also observed other features. Scooter, a bright triangular cloud that moved even faster than the Great Dark Spot. And the small dark spot, nicknamed the Wizard's Eye. But here is the astonishing thing. By 1994, when the Hubble Space Telescope turned its gaze to Neptune, the Great Dark Spot had completely vanished. The storm that had dominated the planet for who knows how long simply ceased to exist. This was shocking. Jupiter's Great Red Spot has raged for at least 300 years, possibly far longer. Yet Neptune's Great Dark Spot lasted less than 5 years after Voyager's discovery. Since then, Hubble has tracked new dark spots appearing every 4 to 6 years, each lasting 2 to 6 years before dissipating. These are not permanent features. They are transient storms that form, evolve, and die on timescales of years. Neptune's atmosphere is far more dynamic than anyone imagined. In 2018, Hubble captured something unprecedented. For the first time, astronomers watched a dark spot form from birth. Bright white precursor clouds appeared 2 to 3 years before the dark oval became visible. This suggests these storms originate deep in the atmosphere, taking years to rise to observable altitudes. Then in August 2020, an even stranger event occurred. A dark spot that had been drifting southward toward the equator, where models predicted it would dissipate, suddenly reversed direction and headed north. This U-turn violated all expectations. A smaller companion storm called Dark Spot Junior appeared briefly, possibly a fragment shed from the main vortex. These observations reveal atmospheric dynamics far more complex than our models can explain. Neptune's brilliant deep azure blue, more vivid than Uranus's pale cyan, has been slightly misunderstood. For decades, enhanced imagery from Voyager created the impression that Neptune appears far bluer than Uranus. But a January 2024 study from Oxford University revealed that in true color, both ice giants appear similar greenish blue, with Neptune only slightly deeper in hue. The difference arises from atmospheric activity. Neptune's dynamic weather produces methane snow that removes aerosol haze particles from the atmosphere. This maintains a thinner haze layer that allows the blue color to shine through vibrantly. Uranus's stagnant atmosphere permits haze buildup, creating a thicker aerosol layer that whitens and pales the appearance. Even the color differences trace back to that fundamental mystery of internal heat. The atmosphere of Neptune consists of 80% hydrogen, 19% helium, and 1 to 2% methane, with traces of water vapor, ammonia, carbon monoxide, and various hydrocarbons produced when ultraviolet light breaks down methane molecules. Clouds stack at different altitudes like floors in a building. Water clouds form at the deepest levels, where temperatures and pressures allow water vapor to condense. Above that, ammonium hydrosulfide clouds drift. At the highest, coldest regions, methane ice cirrus clouds form delicate wisps. These high-altitude clouds are so elevated that they cast shadows on the cloud deck below. Voyager captured images of these shadows extending 56 kilometers downward. That is the vertical depth of Neptune's atmosphere made visible. Neptune's internal heat remains the key to everything. But why does Neptune possess this heat while Uranus does not? They formed at roughly the same time from the same materials. The leading explanation circles back to migration and impacts. During the chaotic early solar system, when planets scattered and migrated, Uranus may have suffered that catastrophic Earth-sized impact that expelled its primordial heat and created insulating layers in the interior. Neptune, following a different migration path, avoided such violence. Its core heat remained intact. Or perhaps compositional differences, dissolved magnesium creating different thermal insulation properties, explain the divergence. The mystery endures. Two twin worlds born together that grew to become opposites. Understanding why is one of planetary science's greatest challenges. Neptune's largest moon dominates its system in every way. Triton contains 99.5% of all mass orbiting the planet. At 2,700 kilometers in diameter, it ranks as the 7th largest moon in the solar system, larger than Pluto. Its surface temperature of minus 235 degrees Celsius places it among the coldest measured places anywhere. Yet this frozen world proves startlingly alive. How can a moon so cold, so far from the sun, show signs of geological activity? The answer lies in Triton's unique orbit and its violent history. This moon should not be where it is. It was not born here. Triton is a captive from the outer darkness. Triton holds one critical distinction. It is the only large moon in the solar system with a retrograde orbit. It circles Neptune opposite the planet's rotation at a 157-degree orbital inclination. This configuration is gravitationally unstable. No moon could form in such an orbit. The conclusion is inescapable. Triton is a captured Kuiper Belt object, likely a Pluto-like dwarf planet that wandered too close to Neptune billions of years ago. Tidal forces during capture would have melted Triton's interior completely. Any original moon system Neptune possessed would have been destroyed in the chaos. The captured moon settled into its current death spiral. In approximately 3.6 billion years, Triton will approach so close that tidal forces will tear it apart, creating a spectacular ring system. When Voyager 2 flew past Triton in August 1989, it discovered something that should not exist on such a cold world: active nitrogen geysers. Plumes of gas and dark particles erupting 8 kilometers high into the tenuous atmosphere. At least 4 distinct plumes were identified during the flyby. The largest, named Mahilani and Healy, spewed nitrogen gas mixed with dark organic compounds at speeds sufficient to carry material 150 kilometers downwind before settling. These eruptions create more than 120 dark streaks across the southern hemisphere. Each streak represents frozen deposits from a geyser that remained active for months or even a year. On one of the coldest surfaces in the solar system, violent eruptions pierce the ice and blast material into space. What powers these geysers? 2 theories compete. The solid greenhouse effect proposes that transparent nitrogen ice allows dim sunlight to penetrate and heat dark material beneath the surface. Pressure builds until explosive release. Alternatively, internal heat from tidal flexing or residual formation heat could drive cryovolcanism, eruptions of water ammonia mixtures from a subsurface ocean. If the latter proves true, Triton joins the exclusive club of ocean worlds. Beneath kilometers of ice, a global ocean of liquid water mixed with ammonia might exist. And in that ocean, shielded from radiation, provided with chemical energy from hydrothermal vents on the seafloor, life might have found a way to begin. Even here, 30 astronomical units from the Sun, life remains possible. Triton's surface ranks as the youngest in the outer solar system. Age estimates range from less than 100 million years to possibly less than 10 million years in some regions. Very few impact craters mar the terrain, indicating continuous resurfacing erases bombardment evidence. The most distinctive feature, visible in Voyager's images, earned the nickname cantaloupe terrain. This dimpled, pitted landscape covers roughly 15% of the surface and appears nowhere else in the solar system. Vast cryovolcanic plains like Cipango Planum span nearly 500,000 square kilometers. Leviathan Patera, an 80-kilometer caldera, demonstrates explosive volcanic activity. 2 enormous cryolava lakes were identified, stable liquid bodies that existed on the surface when they were molten. Triton is geologically active now, not billions of years ago. Now, a thin atmosphere envelops Triton, though calling it thin understates the case. Surface pressure measures only 1.4 to 1.9 pascals. That is 1/70,000th of Earth's atmospheric pressure. You could not breathe it. You would not feel it as wind on your skin. Yet this wispy envelope exists, consisting mostly of nitrogen with traces of methane and carbon monoxide. Nitrogen ice crystal clouds drift in the lower atmosphere. Organic haze layers, produced by ultraviolet breakdown of methane, float at higher altitudes. The South Polar region displays a pink-hued nitrogen ice cap. And mysteriously, Triton's upper atmosphere is growing warmer. Temperatures have increased significantly since Voyager's measurements. We do not know why. Neptune's ring system appears delicate compared to Saturn's brilliant bands. 5 main rings extend from 41,900 kilometers to 62,930 kilometers from the planet's center. The outermost ring, Adams, contains the system's most distinctive feature. Instead of a uniform band of particles circling the planet, bright arcs confine themselves to just 40 to 45 degrees of longitude. These arcs bear names from the French Revolution motto: Liberté, Égalité, Fraternité, and Courage. By orbital mechanics, these concentrated clumps should spread uniformly around the ring within years. They persist. The shepherd moon Galatea provides gravitational confinement through a complex resonance. But the arcs are unstable. They are evolving rapidly. They may vanish within a century. Between 1989 and 2009, the arcs changed dramatically. Liberté nearly disappeared. Courage jumped 8 degrees forward in its orbital position. By 2009, both Courage and Liberté had vanished from observations, leaving only Fraternité and Égalité visible. Ring composition consists of extremely dark material with an albedo of only 6 to 10%, likely organic compounds, radiation processed from methane ice, mixed with 20 to 70% dust. If current decay continues at the observed rate, Neptune's ring arcs will disappear entirely within 100 years. We are witnessing the death of a ring system in real time. The Neptune system, like all things, is not eternal. It evolves, changes, and one day it will be gone. We return to the central enigma. Uranus and Neptune are nearly identical twins. They have almost the same size, nearly the same mass, presumably the same composition. They formed in the same region of the early solar system from the same primordial materials, yet they behave as opposites. Neptune radiates 2.6 times more energy than it receives from the sun, maintaining a powerful internal heat engine. Uranus barely emits 15% excess heat, essentially running on sunlight alone. This single difference cascades through every observable property. It shapes their atmospheres, drives their weather, determines their activity levels. Why do two planets so similar in structure diverge so dramatically in behavior? This question haunts planetary science. The giant impact hypothesis offers one explanation. The collision that knocked Uranus onto its side likely expelled most of the planet's primordial formation heat. When a world forms, gravitational energy converts to heat. The young planet glows. Over billions of years, this heat slowly radiates away. But if a massive impact occurs early enough, it can blast that heat into space prematurely. The impact may also have deposited debris around the core, creating insulation layers that trap whatever core heat remains. Meanwhile, Neptune, following a different migration path through the chaotic early solar system, avoided such catastrophic violence. Its primordial heat remained intact. Its interior stayed hot. The divergence began 4 billion years ago with a single violent event, but impact history may not tell the whole story. Recent research in 2021 from Arizona State University revealed that, at ice giant interior conditions, water can dissolve magnesium from rocky minerals. If Uranus accumulated more dissolved magnesium than Neptune, this would create thermal insulation layers that prevent heat from escaping the core through convection. The magnesium-rich layer acts like a blanket wrapped around the core. Heat cannot rise. Convection stalls. The interior stratifies into separate zones with minimal mixing. Neptune's interior, with less magnesium, allows heat to flow freely through convection currents. The difference may come down to subtle variations in composition, small differences that produce enormous consequences. The 2024 breakthrough from UC Berkeley added another piece to the puzzle. Computer simulations show that water and hydrocarbons naturally separate into two immiscible liquid layers under ice giant conditions, just like oil and water on Earth. Water-rich layer floats above a carbon-nitrogen, hydrogen-rich lower layer. This stratification prevents large-scale convection cells from forming. If Uranus has more pronounced layering than Neptune, heat transport from core to surface would be severely limited. Neptune's more mixed interior allows vigorous convection. This compositional layering also explains both planets' bizarre magnetic field geometries. A thin convecting outer shell generates chaotic multipolar fields instead of organized dipoles. Structure shapes behavior. Composition determines destiny. These theories are not mutually exclusive. Perhaps all contribute. The giant impact expelled Uranus's primordial heat. Dissolved magnesium created insulation layers. Immiscible fluid stratification prevented convection. Meanwhile, Neptune escaped the impact, accumulated less magnesium, and maintained better interior mixing. Small differences compounded over billions of years. What began as subtle variations became fundamental divergence. This is how planets evolve. Not through single causes, but through the complex interplay of impacts, composition, thermal evolution, and time. Uranus and Neptune teach us that even twin worlds can follow different paths. That initial conditions matter. That history shapes the present in ways we are only beginning to understand. Understanding this mystery extends beyond academic curiosity. Neptune-sized exoplanets are the most common planetary type in the galaxy. 30% of confirmed exoplanets fall into this size range, with another 30% being super-Earths and mini-Neptunes. There exists a radius valley in exoplanet-sized distributions around 1.5 to 2 Earth radii, where smaller planets lose hydrogen-helium atmospheres and become super-Earths, while larger ones retain atmospheres and become mini-Neptunes. Uranus and Neptune provide the only nearby laboratories for studying this crucial transition. Everything we learn about local ice giants informs our interpretation of thousands of exoplanet observations. These two worlds in our outer solar system are Rosetta Stones for understanding planetary systems everywhere. Neither planet formed where we find it today. The NICE model, developed over the past 2 decades, demonstrates that ice giants must have formed much closer to the Sun. At current distances of 19 and 30 astronomical units, insufficient material density exists to build 15 to 17 Earth-mass planets within the solar system's lifetime. Instead, Uranus and Neptune likely formed between Jupiter and Saturn at 8 to 15 astronomical units from the Sun. Only later, during a chaotic period of planetary migration and gravitational scattering, were they flung outward to their current orbits. This migration explains captured moons, Kuiper belt structure, Trojan asteroids, and the late heavy bombardment. These worlds are not where they were born. They are refugees from the inner system. Some models suggest a 5th giant planet once existed. During the chaotic migration period, this ice giant encountered Jupiter and was ejected from the solar system entirely, becoming a rogue planet drifting through interstellar space. If true, our solar system once had 5 giants, not 4. We lost one to the darkness. The others were scattered to their current positions. Uranus and Neptune are survivors of a violent reshuffling that occurred 600 million years after the planets first formed. They carry the scars of that violence still. Uranus rolls on its side. Neptune glows with internal fire. And somewhere in the galaxy, if it still exists, a 5th ice giant wanders alone between the stars, forever exiled from the Sun. For 140 years after Neptune's discovery, these worlds remained mysterious blue dots in even the most powerful telescopes. Then humanity accomplished something extraordinary. Voyager 2, launched August 20th, 1977, took advantage of a rare planetary alignment occurring once every 175 years. Using gravity assists from each giant planet, the spacecraft could reach all 4 outer worlds in a single grand tour. It flew past Jupiter, then Saturn, then continued where no probe had gone before. Uranus in 1986, Neptune in 1989. These remain humanity's only close encounters with the ice giants. Everything we know about these worlds comes from those brief flybys. Voyager 2 approached Uranus on January 24, 1986, passing within 81,500 kilometers of the cloud tops. The encounter proved challenging. Only 5.5 hours of close study during the flyby. The spacecraft arrived during southern summer, when the South Pole faced the Sun and the North Pole remained in complete darkness. Voyager could only image the southern hemisphere. Everything we know about northern Uranus comes from later telescope observations or remains unknown. Still, the discoveries astonished. 10 new moons, bringing the total to 15. 2 new rings confirmed. The rotation period measured at 17 hours, 14 minutes. And that extraordinary magnetic field tilted 59 degrees from the rotation axis. The planet appeared remarkably bland in visible light, a nearly featureless cyan disk. Crucial detail emerged only in 2024. Researchers analyzing Voyager's magnetic field data realized the spacecraft arrived during a rare solar wind compression event that occurs less than 5% of the time. The magnetosphere appeared atypically compressed and plasma depleted because of this unusual solar activity. For 38 years, our understanding of Uranus's magnetosphere was based on a snapshot taken during abnormal conditions. This revelation means much of what we thought we knew about Uranus's space environment may be wrong. The planet likely has a more robust magnetosphere than Voyager observed. It may possess radiation belts we never detected. The moons may interact with the magnetic field in ways we have not seen. One brief flyby during unusual conditions shaped decades of understanding. The Neptune encounter on August 25, 1989, brought Voyager 2 within 4,800 kilometers of the North Pole, the closest approach to any planet during the entire mission. Despite receiving only 3% of the light levels at Jupiter, all 10 instruments continued functioning flawlessly. The discoveries came rapidly. 6 new moons, including Proteus, larger than previously known Nereid but hidden in Neptune's glare. The complete ring system confirmed with its mysterious arcs. Those record-breaking 2,100 km/h winds around the Great Dark Spot. Triton's active nitrogen geysers and bizarre cantaloupe terrain. Neptune proved far more active than anyone predicted. In just a few hours, Voyager rewrote the textbooks on ice giant worlds. After Neptune, Voyager 2 continued into interstellar space. It is now more than 20 billion kilometers from Earth, still transmitting data through the Deep Space Network. The spacecraft carries a golden record containing sounds and images from Earth, a message to any intelligence that might find it in the distant future. Voyager 1 and 2 are humanity's most distant ambassadors, carrying our story into the cosmos. But their encounters with Uranus and Neptune lasted only hours. Imagine learning everything about Earth from a 5-hour flyby. You would miss so much. The seasons. The weather patterns over years. Long-term changes. We face the same limitation with the ice giants. Everything we know comes from brief snapshots that may not represent normal conditions. Since Voyager, the Hubble Space Telescope revolutionized ice giant science. Its outer planet. Atmosphere's Legacy program captures annual global maps tracking seasonal changes and transitory events. A 20-year study revealed methane strongly depleted near Uranus's poles with dramatic aerosol changes. The North Polar region brightens significantly as the planet approaches northern summer solstice in 2028. Hubble documented multiple Neptune dark spots, including the 2018 discovery that revealed precursor white clouds appearing 2 to 3 years before dark ovals materialize. Ground-based observatories using adaptive optics matched Hubble's resolution. Keck Observatory made the first infrared detection of Uranus auroras in 2023. We learned more about these worlds from Earth than Voyager taught us. But an orbiter would teach us far more still. The James Webb Space Telescope's observations from 2022 to 2025 represent the most significant advance since Voyager. Webb's infrared vision revealed 11 of Uranus's 13 rings with unprecedented clarity, including the faint dusty Zeta and Nu rings invisible since Voyager. Atmospheric features appeared that earlier instruments could not detect. A bright polar cap, subtle brightening near the North Pole, bright clouds at the polar cap edge. For Neptune, Webb provided the clearest ring views in 30 years, capturing all 5 rings including the dust bands and visible arcs. But the breakthrough came in June 2023. Webb detected Neptune's auroras for the first time, identifying hydrogen-trihydrogen cation emissions at mid-latitudes rather than poles. The planet's upper atmosphere has mysteriously cooled by hundreds of degrees since Voyager measured temperatures. Webb also discovered Uranus's 29th moon in February 2025, a 10-kilometer object designated S2025U1. Ground-based telescopes added 3 more moons in 2023 and 2024 using Magellan and other facilities. The continued discovery of tiny moons decades after Voyager demonstrates how much remains unknown. Each new moon hints at violent collisional history, ongoing ring-moon interactions, complex dynamical evolution. These systems are not static. They evolve. They surprise us. And every observation raises as many questions as answers. We have learned much in the decades since Voyager. We have also learned how little we truly know. The ice giants guard their secrets well. The 2023 Planetary Science Decadal Survey made a historic recommendation. A Uranus orbiter and probe mission was identified as the highest priority flagship class mission for the next decade, chosen over Neptune, Odyssey, and Enceladus Orbolander concepts. This would be the first dedicated ice giant orbiter, following in the tradition of Galileo at Jupiter and Cassini at Saturn. The roughly $4.2 billion mission would carry an orbiter with 50 kilograms of instruments, plus an atmospheric probe that would descend through Uranus's atmosphere measuring composition, temperature, pressure, and wind speeds at various depths. During a 4.5-year science phase, the orbiter would transform our understanding of these mysterious worlds. The mission would conduct multiple flybys of each major moon, searching for subsurface oceans through gravitational and magnetic induction signatures. It would map the magnetic field geometry in detail, finally resolving the strange offset and tilt. It would measure gravitational moments to constrain interior structure. It would track atmospheric dynamics through multiple Uranian years. The probe would directly measure noble gas abundances and isotope ratios, data crucial for determining where and how Uranus formed. Vertical profiles of water, methane, and ammonia would constrain interior composition models. Measurements of heat flux at depth would resolve whether Uranus truly lacks internal heat or whether insulation layers trap it below observable levels. Every scientific question we have asked could be answered, but timing is critical. The optimal launch window opens in the early 2031 to 2034 period. A Jupiter gravity assist during this window can reduce travel time to approximately 13 years, enabling arrival around 2044 to 2047 during Uranus's equinox. At equinox, the sun illuminates all latitudes. Both poles receive sunlight. The entire planet becomes accessible. Rings, moons, atmospheric features at all latitudes can be studied. Miss. This window and portions of the planet slip into decades of darkness. The next Jupiter alignment opportunity does not occur for another 12 to 13 years. And a spacecraft arriving then would find one hemisphere shrouded in night, just as Voyager did. The window is narrow, the opportunity fleeting. Current timelines suggest a mid to late 2030s launch due to plutonium-238 shortages for radioisotope thermoelectric generators. Solar panels cannot provide sufficient power at 19 astronomical units, where solar flux measures only 3.69 watts per square meter compared to Earth's 1,360. The spacecraft needs nuclear power to survive. Production of plutonium-238 is being ramped up, but supplies remain limited. This constraint affects all outer solar system missions. The irony is bitter. We have the technology to build the spacecraft. We have the scientific rationale. We have the funding commitment. What we lack is the fuel. And because of this shortage, the launch may slip beyond the optimal window. Time is running out. The scientific objectives address fundamental mysteries. How do ice giants form and evolve? What drives the temperature difference between Uranus and Neptune? What generates their bizarre magnetic fields? Do the major moons harbor subsurface oceans? What causes the atmospheric energy crisis where temperatures exceed radiative equilibrium? How do seasons lasting decades affect atmospheric dynamics? What is the composition and state of the deep interior? These are not academic questions. They inform our understanding of planetary formation throughout the galaxy. Giant-sized worlds are the most common exoplanet type. We cannot understand exoplanets without understanding our local examples. And we cannot understand our local examples without a dedicated mission. The European Space Agency's Voyage 2050 program identified ice giant exploration as a strategic cornerstone. International cooperation could expand scientific capabilities and spread costs. Communications infrastructure, perhaps a separate element studying Neptune while NASA focuses on Uranus. The Cassini-Huygens mission demonstrated how powerfully international collaboration can advance planetary science. Imagine two orbiters launched a few years apart, one to each ice giant, coordinated observations revealing how these twin worlds diverged. We could compare atmospheres in real time, track storms on both planets simultaneously, measure internal heat flow with identical instruments. The scientific return would be extraordinary, but it requires commitment from multiple space agencies. And it requires action soon. If we fail to launch by the mid-2030s, another generation waits. Young scientists starting their careers today would reach retirement before the next optimal opportunity. Students inspired by the mission would grow old waiting for results. The cost of delay is measured not just in years, but in lost opportunities to characterize thousands of exoplanets. Every Neptune-sized world discovered orbiting other stars will remain poorly understood because we lack ground truth from our own ice giants. The urgency is real. The window is closing. And the decision to act or delay will be made in the next few years. This is our moment. This is our chance. We must take it. The mission addresses astrobiology questions about ocean world habitability. If Miranda, Ariel, or Titania harbor subsurface oceans, life might exist in those hidden seas. Even Triton, captured from the Kuiper Belt, might host a global ocean beneath its icy shell. These would be habitable environments sustained not by sunlight, but by tidal heating and chemical energy. Life, if it exists, would be utterly alien, adapted to crushing pressure, perpetual darkness, and temperatures barely above freezing. Life is tenacious. Life finds a way. If we discover that ocean worlds exist throughout the ice giant systems, it would revolutionize our understanding of where life can arise. The search for life in the universe may not end on Mars or Europa. It might take us to the ice giants. Recent discoveries shatter assumptions built on Voyager's single snapshot. Neptune's upper atmosphere cooled by hundreds of degrees between 1989 and 2023. This reveals these worlds remain dynamic over human timescales despite their distance from the Sun. The cooling correlates with an 11-year solar cycle discovered in 2022 studies. Neptune's mid-infrared brightness follows solar activity, an unexpected coupling between the solar wind and an atmosphere 30 astronomical units away. How does the Sun influence Neptune so profoundly across such vast distances? We do not yet know. Every answer spawns new questions. The mysteries multiply faster than we can solve them. Dark spots that reverse direction defy atmospheric models. When the 2020 spot performed its unprecedented U-turn, it challenged 30 years of assumptions about vortex dynamics. The appearance of Dark Spot Jr. as an apparent fragment suggests these storms are more complex than we imagined. Perhaps they are multi-component systems. Perhaps they interact with deep atmospheric layers we cannot observe. Perhaps Neptune's internal heat drives convection currents that catch and redirect these storms in ways our models do not capture. Uranus's increasing activity as it approaches equinox demonstrates profound seasonal forcing. The planet no longer appears featureless. Storm systems now routinely appear in telescope images. This seasonal evolution over decades provides a unique laboratory for studying atmospheric response to extreme insolation variations. The continued discovery of tiny moons decades after Voyager demonstrates how much remains unknown. Each new moon hints at violent collisional history, ongoing ring-moon interactions, complex dynamical evolution. S2021 N1, Neptune's outermost moon with a 27-year orbit, holds the record for the most distant moon from its parent planet in the solar system. How many more objects orbit undetected in the darkness? How many more moons await discovery? The ice giant systems are not well-explored territories. They are frontiers, terra incognita, blank spaces on the map waiting to be filled. And every time we look more carefully, we find something new. Something unexpected. Something that forces us to reconsider what we thought we knew. Auroral detections on both planets required cutting-edge infrared instruments and decades of telescope development. The mid-latitude location due to tilted magnetic fields creates unique magnetosphere, ionosphere coupling. These auroras may contribute to the energy crisis, the mystery of why upper atmospheres remain warmer than models predict through Joule heating at unusual latitudes. Magnetic field mysteries found partial resolution through 2024 computational breakthroughs showing immiscible layer formation. But questions remain. What are exact transport properties under realistic compositions? How does supersonic ice affect convection? Does diamond rain occur throughout the mantle or only in specific zones? What happens at the core mantle boundary? The breakthrough answered some questions and revealed how many more we must ask. Interior composition remains highly uncertain. Rock-to-ice ratios could vary dramatically from current models. Recent debates question whether ice giants might actually be rock giants with higher silicate content. The degree of differentiation, whether distinct layers exist or gradual composition gradients, remains unknown. Core state, composition, and even mass carry large error bars. We do not know what is inside these planets. It can build models, and it can run simulations. But without seismic data, without measurements of internal magnetic fields, without gravity measurements from an orbiter, the interior remains a black box. We are trying to understand a clock without opening the case. Hear it ticking. We can guess at the mechanism. They cannot be sure. Atmospheric mysteries multiply. How do dark spots form at depth, and why do they dissipate? What triggers precursor white clouds years before spots become visible? Why do some storms reverse direction? How deep do winds extend, and what drives Neptune's supersonic velocities with minimal solar input? What causes the stratospheric energy crisis? How do aerosol hazes contribute to heating? What role do inertia gravity waves play in energy transport? Each question connects to others. Atmospheric dynamics. Couple to interior heat flow. Magnetic fields affect charged particle precipitation. Chemistry determines cloud properties. Everything influences everything else. The system is coupled, complex, chaotic. Understanding it requires long-term observations from orbit. Snapshots are not enough. We need to watch these worlds through complete seasonal cycles. Formation questions persist. Did Uranus and Neptune form in situ or migrate from closer to the Sun? The NICE model provides a framework, but uncertainties remain. Exact formation locations, growth timescales. The role of pebble versus planetesimal accretion. When did the giant impacts occur? Was Uranus the only victim, or did Neptune experience similar collisions? How did these impacts affect thermal evolution? The discovery that supersonic ice exists throughout the mantle, confirmed only in 2019, revolutionized interior models. Yet questions about this exotic phase remain. What are exact transport properties mixing water, ammonia, and methane? How does supersonic ice affect convection? These are not esoteric questions. They determine how heat flows through the planet. They control whether worlds stay warm or freeze. Uranus and Neptune stand as the least explored major planets, visited only once during fleeting flybys. Yet they harbor physics found nowhere else. Diamond rain falling through electrically conductive oceans, magnetic fields that defy planetary norms, atmospheres with energy budgets that violate radiative balance, moons with possible subsurface oceans receiving 1/900th of Earth's sunlight. These worlds represent the most common planetary type in the galaxy. Neptune-sized planets orbit distant stars throughout the Milky Way. Understanding our local ice giants teaches us about worlds light years away. They are not just planets. They are keys to understanding planetary systems everywhere. They are laboratories where nature performs experiments we cannot recreate on Earth. They are waiting for us to return. We have traveled together from Earth to the edge of the solar system. We have explored worlds that roll through space and worlds that rage against the darkness. We have descended through exotic atmospheres into interiors of impossible physics. We have seen moons that should be dead yet erupt with geysers. We have witnessed diamonds falling like rain and magnetic fields that defy convention. And throughout this journey, one truth has emerged again and again. We barely understand these places. They are not well-studied worlds with a few remaining mysteries. They are profound mysteries with a few sparse observations. Everything about them challenges our understanding of how planets work. Consider what we do not know. We do not know why Uranus radiates almost no internal heat. We do not know what drives Neptune's supersonic winds. We do not know how dark spots form or why they dissipate. We do not know the exact composition of the interiors. We do not know if the major moons harbor oceans. We do not know how the bizarre magnetic fields couple to the atmospheres. We do not know where these planets formed or exactly how they migrated. We do not know if diamond rain truly occurs or if it is merely theoretical. We do not know the precise temperature, pressure, and composition profiles at depth. After decades of study, the list of unknowns dwarfs the list of established facts. This is not failure. This is the frontier of knowledge. This is what exploration feels like. When we landed on the moon, we thought we understood lunar geology. Then we collected samples and realized how wrong we were. When Pioneer and Voyager flew past Jupiter and Saturn, they revealed worlds utterly unlike our models predicted. Science advances not through confirming what we think we know, but through discovering how much we do not know. Uranus and Neptune are teaching us humility. They are showing us that planets are more diverse, more complex, more surprising than our theories suggest. And that is exactly what we need. Humility before nature. Recognition that the universe will always exceed our imagination. The James Webb Space Telescope continues revealing surprises. Auroras, cooling atmospheres, tiny moons, dynamic storms. Atmospheric features invisible to earlier instruments. Each discovery raises new questions. Why did the upper atmosphere cool? What drives the auroral activity at mid-latitudes? How many more moons orbit undetected? What causes the storms to form years before becoming visible? Webb is transforming our understanding, but it observes from Earth orbit. It sees only the surfaces of these worlds. To truly understand ice giants, we must send a dedicated mission, an orbiter that can watch for years, a probe that can sample the atmosphere directly, instruments that can map magnetic fields and gravitational variations. Nothing less will suffice. The Uranus Orbiter and Probe mission represents more than scientific investigation. It represents humanity's commitment to understanding our cosmic context. We are a species that explores. We cross oceans and climb mountains not because they are easy, but because they are there. We build telescopes and spacecraft not for profit, but for knowledge. We ask questions not to satisfy practical needs, but to understand our place in the universe. The ice giants call to us not with promises of resources or habitable environments, but with mysteries, pure mysteries, questions that ignite curiosity and demand answers. In an age of immediate gratification and short-term thinking, deep space exploration requires patience, commitment, and faith in the value of knowledge itself. These worlds test our theories about planetary formation, evolution, and dynamics. They challenge our understanding of magnetic field generation, atmospheric physics, and interior structure. They provide the only nearby examples of the most common planetary type in the galaxy. Everything we learn about Uranus and Neptune informs our interpretation of exoplanet observations. When we detect a Neptune-sized world orbiting a distant star and measure its radius and mass, we use Uranus and Neptune as templates for interpretation. When we observe an exoplanet atmosphere and see methane absorption, we think of these blue worlds. When we calculate how heat flows through a planetary interior, we test our models against Neptune's behavior. The ice giants are not isolated curiosities. They are fundamental to planetary science. The window for launch approaches. The early 2030s represent the optimal opportunity. Miss it, and we wait another decade for the next alignment. By then, some of the scientists who advocated for this mission will have retired. Some will have passed away. New generation will take up the cause. but time lost is knowledge postponed. Every year we delay is another year. Thousands of exoplanets remain poorly understood because we lack ground truth from our own ice giants. The cost is not measured in dollars alone, but in lost scientific opportunities, in questions unanswered, in mysteries unsolved. The universe will not wait for us to be ready. The planetary alignments proceed whether we launch spacecraft or not. The choice is ours. As our journey together nears its end, reflect on what we have seen. Two worlds that should be twins but are opposites. Planets that harbor the strangest physics in the solar system. Moons that may hide oceans beneath ice. Rings that will vanish within a century. Atmospheres that defy our models. Magnetic fields that challenge our theories. And above all, mysteries. Beautiful, profound mysteries that remind us how much we have yet to learn. Uranus and Neptune wait at the edge of our solar system, patient and silent. They have been there for 4.5 billion years. They will be there for billions more. But our window to explore them with this generation's technology is narrow. Let us not squander it. Our solar system may be unusual. Most planetary systems discovered around other stars differ dramatically from ours. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, larger than Earth but smaller than Neptune, dominate the census. Compact systems pack multiple planets into spaces smaller than Mercury's orbit. In this cosmic diversity, Neptune-sized planets appear everywhere. They orbit red dwarfs and sun-like stars and massive type stars. They populate the habitable zones and drift in the frozen outer reaches. They are common, perhaps even the default setting for planet formation. And every one of them is a mystery we can only begin to unravel by understanding our local examples. The radius valley in exoplanet populations tells a story. At around 1.5 to 2 Earth radii, a gap appears in the size distribution. Smaller planets have lost their hydrogen-helium atmospheres through photoevaporation and become super-Earths, while larger planets retain their gaseous envelopes and become mini-Neptunes. This process, driven by intense stellar radiation, shapes the demographics of planets throughout the galaxy. Uranus and Neptune are our local examples of worlds that grew large enough to hold onto their primordial atmospheres, providing us with a laboratory to study the very processes that determine whether a world becomes a rocky Earth or a gaseous Neptune. They sit right at the transition point, the gatekeepers of planetary evolution. The James Webb Space Telescope is already giving us glimpses into these distant Neptunes. We have detected water vapor in their atmospheres. We have observed worlds like GJ3470b losing their atmospheres 100 times faster than expected, bleeding gas into space as they orbit their stars. Each piece of data, each spectrum of light from a world light years away, is interpreted through models built on what we know about Uranus and Neptune. Without our local ice giants, these distant observations would be numbers without context. Uranus and Neptune provide the ground truth, the Rosetta Stone we use to translate the light from 1,000 other worlds. Sometimes the process of atmospheric stripping goes all the way. Imagine an ice giant that migrates too close to its star, its entire atmosphere and icy mantle boiled away over millions of years, leaving only the naked core behind. Astronomers call these hypothetical worlds Chthonian planets. And in 2020, we may have found one. 2I-849b is a planet of 40 Earth masses, but with a density similar to Earth's. It may be the exposed core of a gas or ice giant that lost its envelope. This bizarre world, orbiting its star in less than a day, might be what the core of Uranus or Neptune looks like, stripped of its majesty and laid bare to the cosmos. By studying this galactic family of ice giants, we learn more about our own home. Solar system is unusual. Lack a super-Earth? We lack a mini Neptune. Our architecture, with small rocky worlds inside and large giants outside, may not be the norm. Perhaps the calm, stable orbits we enjoy are rare. Perhaps the universe prefers to build worlds like Neptune and then scatter them through their systems in a chaotic dance. By understanding the most common type of planet in the galaxy, we better appreciate what makes our own solar system so special. So suited for the quiet evolution of life on a small blue world, so the next time you look up at the night sky, remember them. Uranus and Neptune, the sleepy giants who may not be sleeping at all. They are our local connection to a galaxy teeming with similar worlds, each with its own story, its own mysteries, its own impossible physics. They are reminders that the universe is not obligated to conform to our expectations. It is wilder, stranger, and more beautiful than we can imagine. The journey to understand it has only just begun. The ice giants wait for us at the edge of everything, guarding the secrets of the cosmos. Future telescopes, even more powerful than Webb, will characterize the atmospheres of thousands of these distant Neptunes. We will build vast libraries of planetary data. But without the detailed ground truth from a mission to Uranus or Neptune, that data will remain full of ambiguities. Are we seeing clouds of methane or something else? Is the temperature profile due to internal heat or stellar irradiation? Our local giants hold the keys to unlocking the secrets of their distant cousins. The more we learn about the worlds next door, the more we can understand the worlds across the entire galaxy. So when you think of our place in the universe, do not just picture Earth alone. Picture our solar system as one of countless possibilities, a system that might be rare in its stability, a system that lacks the most common type of planet. We live in an unusual home. Understanding the ice giants is not just about them, it is about understanding what makes our own world different. It is about appreciating the specific chain of events, the specific planetary architecture that allowed a world like Earth to exist and for life to flourish. The sleepy giants at the edge of our system teach us as much about ourselves as they do about the cosmos. Our long journey to the edge of the solar system is over, but the light from these distant worlds continues its patient travel across the cosmos. When you feel lost in the noise of everyday life, remember the silence of deep space. Remember the planet that rolls on its side and the one that rages with supersonic winds. Remember that the universe builds worlds in ways we are only beginning to comprehend. We are a part of this grand cosmic story, a brief moment of awareness in an ocean of time. What does it mean to you to know that such strange and beautiful places exist waiting for us to explore them?